Thanks very much for the introduction. And you always say whenever you give a talk, it's a pleasure to be here. But you know, I'm finishing a 3-week family tour of Iceland, so it's really a pleasure to be here. Even though the weather could be a bit more sunny, but you know that's. I'm going to on Sunday. I'm flying back to Tel Aviv, which will be 30 degrees centigrade, so I will miss the weather here. So I'm not complaining. I saw some really stunning views. Okay, so the title of the talk is Computer Science 1001.py. I'll explain the name in a second. It's a topics-based introduction to computer science, and much of the work and the talk is based on joint work with Rani Hod, who was the teaching assistant in the first 3 rounds of this when we developed the course, and I always introduced him as the Python guru. I know by now, I mean, we use Python, and I know Python quite well. When I started it, I didn't know it so well, and definitely it was good to have a guru on the team. Okay, as of last year's May, the course is on YouTube. I mean, the recording of the class are on YouTube, but unfortunately they're in Hebrew, so that won't help you a lot. But all the slides, actually, the PDF slides, part of which I'm using in this talk, but all the topics they're all in English, and they're all online, so you could just look at CS1001.py, and you could use them freely if you wish. I'll be happy to get comments and so on. Okay, so as Bjorni just said, I did some things in cryptography and I'm still quite active, trying to be active in bioinformatics, but I'm also quite interested in teaching from things having to do with high school kids, computer science, but also university. So I'm interested in investing some energy in developing these things. So let me give some background of this course in Tel Aviv University. So we are teaching extended introduction to computer science. That's actually why usually CS101 is introduction to computer science, but we say it's 1001 to make sure it's an extended version. And .py is because we use Python for reasons I'll talk about later. So Python files usually end with .py. So that's how we name the course. Okay, so Extended Intro to Computer Science is a required course for all first-year computer science students at Tel Aviv University, being single major or double major. I think about half of our students are double major, including some weird combinations, like I had a master's student who did undergrad in computer science and composition and music and things of that form. Well, actually, I think that's usually a good combination, these double things. Okay, you'll see the course. I mean, I got comments. I gave this talk a number of places in Israel and abroad, and I got comments that it's a very demanding course. It is indeed a demanding course. I think we could afford to do it because admission to computer science in Israel is quite competitive. Everybody, probably in Iceland as well, thinks that they'll do a computer science degree. They'll become, the new Bill Gates or something. So computer science is in high demand, and we have limited spaces. Most universities do, so we could place the bar quite high. So I think many of the students that are accepted to computer science and take this course are really very good. Okay, the course is a 1-semester course. The semester in Israel varies for different reasons. Jewish holidays, wars, strikes of students, strike of faculty, whatever. So 13 to 14 is optimistic. It could be, in my career, quite so many years in university, we probably had even 10 weeks semesters, but the average, the optimistic version is 13 to 14 weeks. And the course has 2 weekly 2-hour lectures, so 4 hours where I stand in front of students, and 2 weekly of recitations with a TA, who is usually a PhD or a master's student. So it's 6 hours of contact with the faculty, with the staff of the course every week. So it's quite multiply that by 13. So it's quite a heavy course. It's not 1 hour a week or something like that. Okay, we taught it. We have computer science in Tel Aviv University probably for 17 or 20 years, and we taught such a course. But in the previous years, we followed very closely the 6001 legendary course of MIT, the Structure and Interpretation of Computer Programs, which use Scheme as a programming language. At some point, some people, including myself, I taught this Scheme version twice, and I wasn't very happy with that. But you're not always happy with everything you do in the university, so that was fine. But I think worldwide, Scheme, I did my PhD at MIT, and when I did it, that was 81 to 85. I think many of the faculty at MIT thought that knowing scheme is the key to your future success in computer science. And I think this has not quite the view today, let's put it that way. I mean, scheme is still being used. I even know people who still program in scheme, but it's not like people thought scheme, AI, lists will be the solution to the future. It's probably not anymore, and even MIT abandoned that. So I actually met a faculty member from MIT, I don't know, 4 years ago or something. We discussed several things, and he told me that they're phasing scheme out. I thought, oh, that's my chance. We could have something, because what they do at MIT is the right thing to do, right? So if they quit scheme, maybe we could quit scheme as well. Okay, so I started to make some noise about maybe we should have a new course. I don't know, here you probably have a somewhat smaller faculty, but some guy from the faculty says you want to do some change. Okay, you get maybe half of the faculty or 1/3 that are somewhat interested enough to attend the meeting. Okay, everybody have a different view. At the end, okay, we agree that we should have some change. But now there is this story about the cat and the mice, that the mice had a party in the kitchen, but then the owner of the apartment brought the cat in. So the mice had a meeting and they said, okay, what should we do? So they decided they should hang a bell on the neck of the cat, and then when he comes in, they'll know that. But then there was a minor question of who will hang the bell. So okay, we should have a change, but who will do the change? So it ended up that I didn't think I was the most appropriate one, but I was ready to do it. So I said, okay, I'll do it. So I suggested as a pilot the program that I'll show you. It was adopted as a pilot. We taught it on an experimental basis, and then after two more runs, it's now adopted as the standard course in Tel Aviv University. Okay, when thinking about it, there are like two major alternatives, and usually I'm being told, okay, this is an introduction to programming. Even Bjarni told me that yesterday and made me really angry. So you could either think of such courses as introduction to programming, or you could think about it as really introduction to computer science, mainly introducing students who want to become rich or whatever, successful in the software industry, to what computer science is about, or at least what we faculty members think it's about. It could be different than what the world thinks it's about, but at least what we think it's about. So the first semester or the second semester, they take it either one of those semesters, get some idea of what the students will get some idea of what they're going to do in the next 3 years. And then maybe some of them will decide it's not what they want to do, but at least, okay, so we chose the second alternative. So it's a topics-based introduction to computer science, and we introduced quite a wide spectrum of topics, including, you'll see soon, some topics that are not even covered at the standard undergraduate curricula. I don't know, compression, for example, or some error correction, things like that. Obviously, if you do such a wide spectrum, I'll show in a few slides, we cover maybe 12 topics. You cannot dive very deeply into any of them. But you could dive, I think, deeply enough that they get a notion of what's going on. Sometimes I have to round the corner, so I don't know, I do Lempel Ziv, I don't do the most efficient thing, I do some slightly inefficient thing, and I tell them, okay, I could compress text of 10,000 characters in a reasonable amount of time. If you want to do 1 million, you have to do some more sophisticated things. You have the tools, but I will not go over it, I don't have enough time. So I do round the corner, but I tell them I round the corner. In some places, we don't round any corner. It's obviously a challenge to explain some of these notions to first-year students, but I think it is workable, and they complain sometimes during the course, but I think at the end of the course they say, maybe a year later, we learned something, which is what I want. I don't want them to be happy during the course, I want them to be happy a year after, to say, we gained something. I mean, I'm not against them being happy during the course, but it's not my main goal.
How many students take the course?
So we have about 300 to 350 first-year students every year, and they split about evenly between first semester and second semester. So, and we have 2 lectures every semester. So it's about 80 to 85 in a class. Not all of them show up, and probably the same thing here, but 80 to 85 are registered. Maybe 90 are registered, and then during the semester, maybe 5 to 10 drop the course, but the rest survive. Okay, and another important, so almost all the topics, maybe except one, that we teach include actual implementation. It's not a theory course. I'm just waving my hand. I mean, theory is beautiful. I did my PhD in theory and so on, but it's definitely not a theory course. It's a course that you do implementation. We give them examples of programs, and they have to do homework, quite demanding homework. We often demonstrate solutions by running code in class. I'll do maybe something very small here, but it takes time, but sometimes I think it's worthwhile because I care about time complexity. We care about time complexity. We examine it both by introducing O notations, which is actually one of the things that students in first year, they do always complain they don't have a good understanding of, even after we made some improvements. But also we actually measure the runtime with a stopper. I mean, Python has like timing, so you measure time before, you run some task. If it's short, you run it 10,000 times. If it's long, you run it once or twice. You measure time after, and you see, and then I compare my implementation, Python's implementation, some inefficient algorithm, efficient algorithm. So we do care about things like time, sometimes about space. And another important goal is that we wanted the course to be exciting and fun, demanding, but also exciting and fun. That should enjoy it. I mean, work hard, but also enjoy it. Sometimes it's conflicting, things, but. Okay, we chose Python as the programming language, what I call vehicle. So, like a driving license, some of you are very young, but those of you who are not that young, I don't think I remember what car I learned to drive on. It doesn't really matter if it's Toyota or a Honda or, I don't know, a Volkswagen. Some people are very religious about programming language. I have a good friend, a colleague of mine who works in high-tech. He did his undergrad with me and worked in high-tech. He probably spent 3 hours trying to convince me that we should do Java. Java is the right thing. I don't know. I'm not very religious about these things. My TA, Rani, who also was my TA previously in crypto course and in computability course, and we worked very well together, and I really wanted him to work with me. He's really a Python guru. He wouldn't go for anything else. So that was definitely something that influenced me. But also I looked at the language. I knew it a little bit. I tried to teach one of my kids a little bit. So Python is almost English. I mean, you could really, if it's a short program, you could read it and understand what's going on. I think that's a big plus. It's interpreted, which means the cycle of developing programs is shorter. The minus thing is it's not very efficient if you have very heavy computational tasks. I don't think that the first year course you need to do, to design missiles or to go into space or something. So I don't think it's a big minus for a first year course, and it's not a bad language to know because definitely more useful than Scheme. I was told that, 1/4 of Google code is written in Python. So it's a language, and then actually students who from the first time or second time we taught it, who already had like job interviews, told me that it helped them, it helps if you know some. It's not a necessary requirement. If you know some language being used, it's helpful. So I think it's not a bad thing. But the same course could be taught in different languages. Just as a comment, MIT moved to their new course, which is called 6.1 or something, is taught in Python. I think CMU also moved to Python. I'm not sure about that. Berkeley moved to Python. Berkeley translated the old Scheme course to Python, and they do it that way, which I think is crazy, but it's bad because I'm being recorded. But anyway, okay, but Python seems to be quite popular among universities who changed the introductory course. There are others, of course. The Technion had a huge argument with a good friend of mine. They're teaching C, using C for the last 20 years, and he told me C is the only thing to do, and so on. And then I think at Hebrew University to do Java. So obviously there are many versions. It's not. Okay, what do I expect from students? Sort of a dual learning outcome. To get a broad view of central subjects in computer science, but also to learn programming. It's not just about ideas, it's also about programming. And we integrate the two things. We explain some idea, here is the idea how you're going to implement it, here is an implementation, a good one, not a good one, and so on. Experiment a little bit, and so it's really well integrated. Okay, this slide is from the first lecture of the course. We will sample 10 to 14 different topics. It should hopefully expose you to some of the beautiful topics and ideas in the field. We won't get into any of them in great depth. We don't have time for that. So some of the ideas we have a very basic image representation and processing. So I had in the end of the class, some students came to me and told me that they really liked it. So I told them we have an advanced real course about image processing. Go take it, and they did it. So it's like you go to a restaurant. Sometimes you've got these, I don't know how do you call it, sample dinners. You have the sample of this and this and that. So really it's a sample of things that are existing, not exhaustive, but existing in computer science. you're interested in that, go take the either required or elective course in this field. Okay. It's not a programming course, yet they will learn Python. And basic idea in programming, like iteration, control structure, recursion, procedure, objects, and so on. So I don't think they miss on anything really, really essential. And I say that Python is relatively new programming. It's not that new. I think it's from the first version from 1990. Now it's the third. We use the third version, but it's relatively new. It definitely is gaining popularity, so it's not a bad thing to know it. Later in their studies, they learn C and C++ and Java. So I think they get some exposure. I think getting some exposure to different languages is not a bad idea. And after you see these 3 or 4 languages, you could probably, on your own, get along with any other, except maybe if it's really weird. Okay, one more thing this course is not about, the famous quote by Dijkstra, the famous computer scientist from Holland. Computer science is about computers no more than astronomy is about telescopes. Don't expect to be able to fix the PC or things of that form after taking this course. You may do it, but it's not about it. But what we do, we do talk about memory and RAM and these things of that form, but not fixing the PC. Okay, so here is in one of the versions what we covered. It's not a complete list. We start by 2 or 3 meetings, so basically a week and a half of Python basics. I start with, print, hello world, or something like that, and then go to loops and assignments and so on. And then we talked about, maybe a non-standard order, but talk about bits and bytes and representation of numbers in the computer. And Python supports, without any modification, supports huge integers. So integers 2,000 digits long or something are just normal. So this leads quite naturally to some primality testing, which I'll show here, and some public key cryptography, Diffie-Hellman key exchange. I do Diffie-Hellman key exchange in week 5 or something like that. So that's and also GCD, greatest common divisor. We do some week or 2 of numerical computation, specifically Newton-Raphson root finding. So we introduce a few ways of trying to find the root of a real value function. Newton-Raphson is one of them, and play a little bit with some parameters there. Representing and manipulating images. Images I found to be really, really nice topic for first year. You look at JPEG or something, you see something mysterious. All it is some metrics. If you just look at gray level, it's just numbers from 0 to 2555. It's very easy to produce synthetic images, to reduce noise locally, not the state of the art. Some reconstructions, and it's very visual, of course. So I think it's really sort of really a chapter that students like. We do some hashing and hash functions, including cuckoo hashing. Okay, I won't talk about cuckoo hashing here, but it's these notions are definitely digestible. Some string matching, including Karp-Rabin probabilistic algorithm for string matching. Okay, this I introduced last time. I think it was good. The halting problem. I talked about the halting problem. One of the reasons that it's usually we do the halting problem showing it's not not decidable and so on. And second year we have a computability course. Somehow when you talk about Turing machines and coding Turing machines, I taught it probably for 10 times, so I know it and so on. But somehow in Python programs are first order objects, so you could have a program having other programs as their input, and it makes it very easy to do this diagonalization, of the proof of theorems. So I am doing it here, but so they're really scared. 1 week before the end of the class, I tell them it's not for the exam, and then they see it again in the computability course, which I also teach. I think they understand it better, because this is this understandability of halting, I think, is one of the gems of computer science. And I got the feeling that many students, when they see it just once, they don't really grasp it. So seeing it twice is not a disaster, I think. Okay, we do some text compression. As I told you, we do Huffman and the codebook and the Lempel-Ziv. Again, Lempel-Ziv, soft version of Lempel-Ziv, not the most efficient, but I basically say, what is Lempel-Ziv? Look at human text, human-generated text. You've got things which are repeated. So instead of repeating it, you say, okay, jump 100 points, 100 characters backwards, and then the next 5 ones just repeat them. And you see that this simple idea just saves you significantly. 40%, 50% of text without doing any more optimization. Simple error correction code we do as well. Okay, I did some secret sharing, played with visual secret sharing when I had the long semester. That's not really necessary. Okay, more things. List data structure is very basic in Python and very convenient. You could slice list, combine list, whatever. Recursion, and we do a lot of recursion. I'll show an example. Lambda expression, one of the opposition when we introduced this new thing, they said, okay, in scheme, lambda, lambda way of defining function, that's really fundamental, and we lose it. Okay, Python supports lambda. We actually use it sometimes. It's actually quite useful. Okay, I won't go over. We do a little bit of object-oriented programming, just classes and methods, no inheritance or anything like that, but I just want them to have a notion of what it is. So I don't know, we have this class of student, and so we generate student names at random and ID at random and also the grade at random. That really scared some people. I told them that's the way we give grades. We just, do at random 20 to 100. And okay, so, but it's a good, okay. So what I want to do is to give you some. Okay, by the way, if there are questions, please ask me now. You don't know. In Iceland, you probably are on the scale of being polite to impolite. In Israel, everybody shouts without even raising his hand. So raise your hand. Don't shout. I will answer. But don't wait till if you have questions. Don't wait till the end. You could ask at the end as well. But okay, so I want to give some snippets from 4 classes to get some feeling of what. Okay, so I start. It's quite in the order that we teach things. So I start with large integer arithmetic and then show probability testing. Hanoi Tower monster, that's a problem that I have invented. Related to Hanoi Towers, but I'll show that. And how is that related to binary search? We see binary search in probably 3 different contexts. One is the standard thing. You've got a list, so searching in a list. If it's sorted, then you do binary search. It's efficient. Otherwise, it's linear. Another is first step for this Newton-Raphson. If you've got a continuous function and you've got a point where it's negative and a point where it's positive, then you could do a binary search on the range to find a problem with a point where it's close enough to 0. And the third one is here. I'll show here. Hashing and cuckoo hashing. I'll show an application of actually of hashing to a problem in bioinformatics of looking for some common subsequences in proteomes. And that problem, I sort of like that problem because it forces you. The proteomes are about 5 million long. So if you do the naive algorithm is quadratic in 5 million, it won't finish. But if you use hashing, it's linear and it finishes in a few seconds. So you really see a difference between efficiency and inefficiency. They actually complained because they implemented inefficiently. The computer, their PCs at home worked for a week, got very hot, and maybe broke down, whatever. But anyway, okay. And then image representation manipulation. I'll give some example. Okay, so large arithmetic, integer arithmetic, and probability testing. That happens at about week 3 of 13 weeks. Okay, so I start by talking. That's actually the first point where I talk about efficiency. So I talk. Let's say we want to do a to the b, raise 2 integers, a raised to the power b. So the naive way to do it is to compute a square, a to the third, and so on. So that takes each time you multiply again. So it takes b minus 1 actually, b minus 1 multiplications. So b minus 1 multiplications. If you're in high school, it sounds good, but if you're probably, most of you are graduate students or faculty members. So a to the b is actually exponential in the length of b. So if b, let's say, is 2 to the 20 minus 17, that takes 20 bits to represent, but it takes over 1 million operations. It's not so great. And if b is 1,000 bits long, then it's completely out of the question. While a number which is 1,000 bits long is not such a huge number. Okay, so this is completely infeasible. Then we explain this iterated squaring idea. So you compute a square, a to the 4. So each time you just square the previous one. And then you just look at the bits where it is 1 and you multiply the appropriate things together. So if you know it, you know it. If you don't, I don't want to go over it, but it's not hard to explain. And I show, for example, if you want to do this raising to a power 2 to the 20 minus 17, then the naive method takes about 1 million multiplications and the efficient method takes about 40 multiplications. That's obviously a difference. Okay, so in principle, we could, raise something to the 2 to the 100 minus 17 power, for example. This is the number if you want to see it. The problem is that the numbers become very big. So, okay, I could do it, but multiplying numbers which are that big, I cannot store them in the computer. Okay, so there's nothing really we could do about that. But then I'm saying, okay, let's do something else. Instead of raising a to the b, let's do a to the b modulus c. So just taking the remainder. So we don't compute it first and then take the remainder, but every step we take the remainder. And this is doable. But the question is, and actually even implementable in Python. It's called POW. I'll show you that if I find it. Okay, so here, POW. POW 325, meaning raise 3 to the power 2, so 3 to the 3 square, modulo 5. So 3 square is 9, modulo 5 is 4. So that's what it gives me. I don't know if you could see anything there, but okay. So the question is this, okay, so I didn't solve the problem I wanted to solve. I do this modular thing. So is that useful for anything? So fortunately it is. Let's view. Full screen. Okay. So the question is this modular exponentiation useful for anything? So fortunately it is. So here I make a small mathematical diversion. There is Fermat little theorem. It says that if P is a prime and A is a number between 1 and P minus 1, then A to the P minus 1 is always 1 modulo P. That's the little theorem of Fermat. This we knew how to prove, many years ago, and actually the proof is elementary. Okay, so what does it give us? So then I talk about prime numbers. Prime numbers are really important in number theory, and they're very important in today's public key cryptography and things like that. So we want to be able to test if a number is prime or not. We do not know how to factor numbers. This we still don't know. It's not that we don't know how to factor numbers. But if I find let's say I've got some m, and I find some a which is between 2 and m minus 1. So I raise a to the m minus 1, and I get something which is not modulo m, and I get something which is not 1. What does that tell me? It tells me the number is not prime. Okay, so let me go back to Python. Let's make some large number. M equal, oops. Okay, you've got a weird keyboard. M equal 2, where is times? Okay. So, okay, 2 to the, what's wrong? This will be the last thing I'll use. So let's say 245 minus 1. Okay, this is m. So I want to check if this m is prime or not. Okay, let's just convince you that m is a large number. It's reasonably large. I could do 1,000. It doesn't want really matter. Okay, so now I want to check if this is a prime or not. So it could be a prime, by the way. So 2 to the some power minus 1 could be a prime, not with such a low probability, but let's hope it's not. Okay, so POW, so this is raising, so I pick some A basically at random. So I pick 17, let's say. So I'll raise 17 to the m minus 1, if I'll find the minus, yes, minus 1, modulo m. Okay, now I hold my breath. Okay, this number, it's not 1, right? It's not 1, that means this m is not a prime. It doesn't tell me anything about the factorization of m, but it tells me m is not a prime. So then the student tell me, how did you pick A? This 17, you were probably very lucky or so on. So then, okay, later I tell them that if m is not a prime, then 90% of all A's will show me that it's not prime, and if not, I will do it twice or thrice, and I talk a little bit about randomized algorithm, and maybe they're not happy about this. It's only randomizing, but okay, so it is useful. Okay, this is some slightly bigger example. So it's a number m, which is 164 digits long. So it's a longer number. You see it here. And I chose something, I don't know, A this time. I chose 65, and obviously this raised to that is not 1, so it's not a prime. Okay, but the proof doesn't give any clue of the factorization. I happen to construct this m as a product of two large primes, but this just because I know it. If I didn't know it, this would not help me. This also shows you something that you could test primality without knowing anything about the factors, which is something which is a bit counterintuitive, right? You think that we talk a little bit about factoring. We show some, this polar draw algorithm, but but not getting very deep in it, but I just say factoring is one of the known hard problems. Okay, so this was one example. The second example is this having to do with recursion and binary search. So I hope you know this game of the Hanoi towers. I mean, Hanoi towers, I think there's no class about recursion which doesn't give Hanoi towers as an example. So you've got these three rods and these rings which have different size, the larger to the smallest, and you stack n of them on one rod, and you want to move all of them to another rod. And the rules is that you could move one ring to another rod, but you are not allowed to put a large ring on top of a small one. And you could in fact show, so there is very, very nice recursive algorithm to do it. The recursive algorithm takes, if you got n rings, it takes 2 to the n minus 1 steps, and you could also show very easily that you always need 2 to the n minus 1 steps. So if n is 200, you cannot span the whole sequence. Okay, so that's the classical Hanoi towers. Now is the monster, the nightmare. So in the middle of the night, your partner put a star, say, we are neutral, we don't know what gender and so on your partner is. Okay, so he wakes you up and say you saw a monster, and the monster demands to know what is the 3 to the 97 plus 19 move in a 200 disks Hanoi tower. Okay, so or else, I don't know what, he will eat him alive or something, or her. Okay, so you know that it takes 2 to the 200 minus 1 moves, so, even if you're very smart and, are accepted to university and so on, it won't help you. I mean, you cannot expand the whole thing. So the monster should find slacks elsewhere. Okay, but the monster is insistent, so, okay, maybe you could devise some idea. Okay, so give it a name, Hanoi move, start via target are the rods, where you start, via what, and n is the number of rings, and k is what is the step. Okay, so now, if k, so remember, probably most of you went through this, so how do you solve it? You first move n minus 1 of the rings to the middle place. Then you move the largest one to the target. Then you move recursively. So if this k happens to be the 2 to the n minus 1 move, so it's just a middle move, so you know what it is. It's moving the largest one to there. Okay, so that's great. But what if it's not? Okay, so if it's not. If it's not exactly the middle move, so we think recursively. If k is the first half, if it's less than 2 to the n minus 1, then you don't care about the bottom ring. You just want to solve a problem with one less ring. If it's more than that, then basically those you already moved. So it's a similar thing. Just you're in the second. Okay, so you think recursively, you solve a problem. Okay, and. Okay, we should keep in mind which rod goes. I mean, the roles of the rods change, but it's not a big idea. Okay, but then I want to put it in sort of larger context and in the context of binary search. So what do we have? We have a really huge space, 2 to the 200 moves space. So if I'm right in the middle, if k is right in the middle, I know what to do. If not, then either I'm the first half or the second half. So I could have the size of the space. So I could, and then having n minus 1 rings. So the execution will be, instead of being exponential in n, it will just be linear in n. So if I have 200 things, the execution will probably take 2 times 200 or something of that form. It will go that deep into recursion. So if either we're right in the middle or we're in the top half or the lower half. So this is sort of something that also, if you think of binary search, or usually binary search, you're either in the top, right in the middle, where you know where you are, or so this is a theme that repeats itself in computer science. And also in this other numerical thing. So we emphasize that. And actually, I don't know how many of you heard about Moshe Feldenkrais. He was a famous Israeli physicist who developed this method of body awareness and movement. And so he said that his method makes the impossible possible, the possible comfortable, and the comfortable pleasant. So in this case, doing this monster thing is really impossible. But using binary search, it makes it possible. And doing binary search, let's say for usual binary search for ordered things, it moves it from possible to comfortable and so on. So I don't know. Anyway, this is Moshe Feldenkrais. he demonstrates something on a skeleton, and that's one of his famous students. I don't know if you know, this is the guy standing on his head is Ben-Gurion, who was the first prime minister of Israel, and he was a student of Feldenkrais. He had terrible back pains, and so Feldenkrais told him, what would you like to do, once I cure you? So standing on my head. So this is a picture of Ben-Gurion standing on his head on Tel Aviv beach. These days, A, Tel Aviv beach is not that empty, and B, you will not find a prime minister in this attire, definitely not standing in his head. So it's something that's changed, but anyway. Okay, third example is hash functions. So we go over dictionary program, where what hashing is used for and so on. I won't go over it here. We do some experiments, actually. I have this object of students, so we hash the students, and then we using chaining, we look for collisions, what's the largest collision, and so on. So they get an idea of some statistical thing that you do things at random, things change, you have some averages, maybe some variance, things of that form. But here I'm using, this is in Hebrew, but here is in English. Basically, we give them, it says assignment, we give them we download for them, because I don't want them to hassle with NCBI, 4 different proteomes of bacteria which are not, I think it's leprosy, cholera, tuberculosis, and salmonella, so it's not bacteria you want to meet in the street. Anyway, and then there, each of them is, the alphabet is 20 amino acids, and each of them, they differ in size, I think between 1.5 million to 5 million or something like that. So it's not huge. It's not a human genome, which is a billions, but it's not negligible. And I asked them to look for longest common subsequences among these proteomes. And actually, these common subsequences, I think leprosy and tuberculosis are quite close, and indeed the common subsequence of those two are much longer than of the other pairs. Bjarni, maybe I'm wrong. Don't correct me, but I think it is correct. But okay. So forget this masquerading of bioinformatics. Now you've got huge strings. You want to find substrings, contiguous substrings, which are the same. So you could do it using quadratic algorithm. Look at all the windows of certain size and try to compare. This will be quadratic in the size, and 5 million quadratic is 25,000 billions. Your computer will not be able to do it. I don't know, maybe NASA computer could do it, but not your computer. Okay, so this won't work. What can work is, suppose you know that the size of the largest common thing is 30. So you could just hash all the 30 mere windows, and when you find collision from here and there, this also takes some thinking, but when you find a collision, and then you should verify it, but you verify that there's no false positive, and then you could do some binary search on the lengths or something like that. So that works even on my old laptop. It works in a matter of, I don't know, half a second or something like that. So first they use hashing here. B, they were exposed to some things which some people think are important, like some bioinformatic databases. And C, they see the importance of efficiency. Okay. So, the last example, I think I'm okay with time, is a little bit about digital image representation. So, by the way, I knew nothing about some of the topics here I knew very well. Some of the topics I knew nothing about. For example, I had no idea how you present an image. I definitely learned something. So I talked to some friends, and so that's an advantage of, having people who know. So they suggested, I wanted to do it, but they suggested specific problems like removing noise and things like that, and then we added other stuff. Okay, any guess what it is?
A boat.
A boat? No. Okay, you'll see it in a second. Yeah, tongue, very good. Whose tongue? Einstein tongue, very good. Magnus. Okay, so this is a portion of Einstein famous. I think I have the picture soon. A portion of this thing, but also only enlarged, so you really see the pixels, right? I mean, each pixel. Usually, the resolution is not so high that the resolution is good enough that you don't see the pictures. Okay. If you want numerically, that's a part of this thing. So there is no. I view this course in some way that demystifying some notions. So what is there in a digital image? If it's gray level, it's basically these numbers. Numbers represent how gray it is. Zero is black. 255 is white, and gray levels in between. If it's color, then you just have 3 of those for red, blue-green. So nothing mysterious. So this thing represents an image, but just it's much nicer to see an image than seeing the numbers. But if you want to manipulate things, it's the numbers. Okay, so this is the indeed portion of this tongue. So first we do some synthetic images. So here, I don't know, I do two loops, one's inside the other, and then the pixel in coordinate ij is c, which is some parameter I have up there, times I plus j mod 256. So 256 is, so basically what do you expect? You expect diagonals to be to have the same, if I add 1 to I and reduce 1 from j, I get the same value, so it will be the same blackness. So I get these things, and if I change C, if C is larger, then I get these things are denser. So, okay, so this is nice to play with. Then some student asked me here if instead of I plus j, I will put I times j, what will happen? So I told him I have no idea, but I have the interpreter in class, so it's no problem. So I just do it. I don't do it here because I don't have, okay, so instead of do I times j, I wanted to center it around, I had 512 by 512 picture, so I want to center it around the middle, so I minus 512 means the middle will be 0. Okay, you get something like that, sort of a fractalic-like thing. I'm not even sure I could completely explain it, but that's, I think, part of the beauty. You get all of sort of nice patterns, I didn't expect to get that. I could probably explain some portion, but then it's fractalic if you look at it. So, and we have something, I don't know, here, I wanted to design something with circular symmetry. So I minus 256 square plus j minus 256 square mod that. So I expect to get some squares. That's what you get. So you get squares, but somehow they're embedded in. I think I could explain it, but it's nice that you get these things and all sort of other functions. Very simple things. You get nice random. You just do things at random. You get just dots of different intensity and so on and so forth. Okay, then we do some weak algorithmic thing. I mean, not demanding algorithmic thing. Discuss Gaussian noise and salt and pepper noise. Salt and pepper noise is you take each pixel and with some probability p, you hit it, either make it completely white or completely black. And the rest you leave. So usually you deal with, 1%, 2%. We could do even more. And then the simplest way to fix errors is local means, so local average around in small frame, or local medians. And then there are advantages and disadvantages to both. They're not the most sophisticated things. I'm not getting any more sophisticated than that. Okay, this is sort of heavy salt and pepper. So it's salt and pepper, I wrote here p equal 0.8. So every pixel gets hit with probability 80%. So half of it gets white, half of it gets wet. Half of it gets black. Okay, so here is, I'm not telling you, but I'll let you guess. I took the original picture here and hit it with this 80% salt or pepper thing. Okay, and this is what happens after I did local medians on that. So anybody wants to guess what the original was? Magnus?
Is that the Dutch painter? No?
Who?
Obama.
Wow! Boy, this guy's amazing. Okay, this is the original. This is after hitting it with this extreme salt and pepper. This is trying the standard local medians, which, okay, good for you, but I didn't see it is Obama. And this is, we have some, not developed, but somebody told us about. And so if you know exactly this is 80% and so on, we could tweak some algorithm that it will. So this is recreated. This is recreated by sort of a strong version of the local medians somehow. I won't talk about it, but it's simple enough that it's so it's good for you. And then I think, you see these things, the things work, and then they're not terribly complicated. Okay, and here is the homework assignment we had, reconstructing shredded images. So DARPA, I think 2 or 3 years ago, had this challenge that they were wondering, you've got these shredders in offices. So you have a top secret, or just a recommendation letter, sent to the head of the department, and then you don't want to just put it in the garbage because somebody may see, so you take it through a shredder. But then, how good is that? There was actually a movie about some U.S. hostages, some people in the U.S. embassy in Iran that managed to escape to the Canadian. The Iranians got shredded pictures of all the employees in the U.S. embassy, and they managed, at least in the movie, they managed to reconstruct it half a minute before these guys boarded some airplane, and it was always. But anyway, it's in DARPA had this challenge. So DARPA they shredded images digitally, including putting damaging some of it. We had a more modest thing. Rani, the TA, he took 20 digital pictures across the campus, cut them between 50 to 200 pieces vertically, permuted them, published the permuted thing, and the task was they had to reconstruct it, and every student who was the first to reconstruct a picture, plus say where it is on campus, it wasn't enough to reconstruct, got some bonus. So at first, this was just after this Protoms, the assignment after this Protom, and the Protom really got them off balance. They were unhappy. So they started complaining. We had a forum, so they started complaining. But then there was one 16 or 15-year-old student in class, and he solved one of them. So they decided it's better to try to get the bonus rather than complain about the tough, stuff. And actually, I think they solved 18 out of the 20. One of the 18 didn't get the bonus because it was a picture of clay, which was hung in my office, and most people didn't visit my office, so they told them, so Rani said in the forum, okay, it's a clay picture, but, is it in the Clay Museum in Chicago? Where is it? So they didn't get, maybe they got half the points or something. But anyway, so it looks like that. That's a shredded thing, shredded and permuted. And then you think about it, basically you devise some measure of, the stripes are different, what the stripes are. So, you have a left side of a stripe and a right side, you devise some measure of similarity, and mostly everything works. So you take the two most similar ones, you put them together, a little bit like in assembly. And then you take the next one and so on, and then you get something which is close enough to what you think it is, and then you go around in campus and try to see, okay, so this, for example, is some real clay chair that was put, I think, in the backyard of the engineering department, and this thing is there's this diaspora museum in Tel Aviv University, so they have this rolling thing which prints some letters, and then it erases it. So I guess it has some symbolic meaning of time and so on. Anyway, so most of it was solved, and at the end they liked it. Not the beginning, but at the end they liked it. Okay, so now I want to talk a little bit about how the students see this course, how we see this course, and some overview of. Okay. Just a few points. I won't go over everything. I think running code in class, like you saw with this primality testing and some other, it's not always a good idea because it takes time and always something gets stuck and so on. But running some code in class, I think, is useful and also could solve problems. Timing, I think, is very important. You really run things and you see how long it takes. We compared efficiency of our own implementation or student implementation, or we do sorting, so sorting, so merge sort or quick sort, and seeing, so okay, all of them are O of n log n, but how efficiently they really are. And we encourage them experimenting, and also encourage, but say that part of experimenting is also making errors. I also make a fair number of errors when I do implement things in class. At the beginning, I had many errors in the presentation. I told them, that's part of a process that you build something new. And I told them, when you program, there is no way you will not make errors. If you are afraid of making errors, go and study something else. So and we encourage them also to look for material online. If they get stuck in some problem, Python is not perfect. There are some corners of Python which are very non-intuitive. Usually, if they have this problem, somebody else said it as well. Some students came to me, and I'm really not an expert, but I told them, okay, let's look it up in Google, and we found explanations. Okay, I'll fix that. Some criticism by the students. Okay, students with no programming background found it very hard. They claimed the pace was too high. I should say, I don't know about Iceland. In Israel, the background of students, probably 1/3 or 1/4 of the class didn't write a line of code beforehand. Probably 1/5 of the class, or maybe 1/6, spend 4 years in the army in some technological unit. They know Python definitely better than I do. They don't know computer science better than I do, but definitely, so for them, Python is no problem. And we're somehow trying to satisfy both. So I'm trying not to bore the guys who know how to program, while losing it's not impossible, but it's not very easy task. So, and definitely the guys who started without knowing had hard time. Most of them coped, but probably a few dropped out. So, okay, some complained that too many topics were covered. Next slide, you'll see others were happy about many topics being covered. So, you get these surveys from 150 students, you get all sort of. Okay, they complained that the load of the homework assignment is too high. They're probably somewhat right. On the other hand, I think if they will say it's not too high, that probably it's way too low. So it's probably you face similar challenges, right? I mean, some of them complained about usage of English in the slides and also in the forum that we had. I told them that you cannot live in computer science without using English. It's neither Icelandic nor Hebrew is the word of computer science. Maybe Chinese will be one day, but this I don't know. But and I don't know Chinese, but maybe some people here do. But I mean, they have to cope with that. Okay, and one thing which I'm not happy about, with 150 students and 7 assignments, we have to use some sort of automatic grading. The automatic grading mechanism we used was very non-tolerable. If you misspell, if you wrote your name Magnus with capital M, with little m instead of capital M, 0. And they were not very happy about that. They were right on one hand. On the other hand, we told them you have to write, Magnus with capital M and capital H and so on. So, if any of you have solutions to this, I will be happy to hear about. I mean, something that works. Okay. Many of them were happy about the course, about the wide exposure, choice of programming language, and so on. Okay, now I'll show off a bit. I got this mail from a student who, actually, this was in March, I was in New Zealand on sabbatical. He wrote to me, he infiltrated to the course somehow, he wanted to learn Python, even though, he was a student of industrial engineering and economy or something like that, and he said that this was the best class I've ever taken in the university. It's really nice. I mean, okay, I show off, but it's really nice to get these things because you really put a lot of effort into such, designing such course. And so not all students go to you and say, but when you get, the odd one or two, or you meet some of them later, it's nice to do. Okay, some reflections. There are some things we want to have a chapter on concurrency. Python supports it to some extent. What we did, the first run I was really not happy about, so I don't know. Maybe we'll do it, maybe we'll leave it. The main problem I face as a teacher is the huge gap in the background of the students. That's a major problem. Overall, we think it's a good course. It's not a very objective thing. In general, we get quite good feedback from students. The fact that the grading is not good is working against us, and the fact that they're working hard working against us. But I do talk to these students in later courses, and I think in general they seem to be reasonably happy. Okay, that's the famous last words from that's the last talk last slide in this from Dr. Seuss. I don't know if you know this. Okay, so basically you learn something, and now go on and do something with it. Okay, that's it. Thank you. Questions?
I was just wondering how it fits in with the rest of the program.
Okay, so far the rest of the program ignored it. Okay, which means like hashing, for example. So we have in data structure they do hashing a lot. So I looked at what they do and what they do I don't teach that course, but what they do in hashing. It's mostly like a theoretical analysis of things. So I didn't do any theoretical analysis. I just told them, I don't know, that the maximum load is log n over log n or something. So they do get to see some, to implement things. And individual students told me that at the beginning, not everybody took it because it was still experimental. So they told me that they felt they're better than the guys who didn't take the course. I guess at the end, the rest of the department will have to acknowledge the fact that we do it, and maybe they want to do something more. Then the halting thing, for example, on purpose, I know that I'm repeating it, and I don't think it's a disaster. It's not a disaster if some of the topics are repeated. I guess in a year or something, we'll do some small revisions on the more advanced course, so maybe we'll drop something, and the others, if they see it twice, it's not, usually not a disaster.
Yeah, so you introduced it as a Python-based course, but...
No, the Python I said is sort of...
It seems to be like an aside, right?
Yeah, the Python is an aside. I mean, you could do it in C or Java or whatever. We happen to like Python or something. It's not... Okay. I mean, I think I could sit with you on a beer and convince you why I think Python is a good choice for a first language, but I don't think it's a crucial decision.
Okay, but I'm curious about that aspect. I mean, why do you think it's the best language?
Okay, I wouldn't even say it's the best language. I think from my limited knowledge, it's good because, I mean, I usually do this if you want to, where is this? If you want to do hello world, okay, so I don't know, in Java it probably takes 2 lines of defining what the input is, or the input file, or whatever. So print, oh, now I will not find, where's the quotes? Oh, good. Okay, that's print hello world. So it's sort of a very simple interface. We restrict ourselves to 1-page code at most. In 1-page code, okay, you could write, 3 lines, which will be unintelligible. But I think if you write it in a reasonable way, it's really easy to read and to find out. And I think the design, if you want to design a program, I think it's easier than in some languages which are compiled. I will not claim, I definitely don't claim it's optimal, and I actually am not qualified to claim it because some fields, somewhat subject I feel I really am an expert on. I'm not an expert on programming language. I just talk to enough people and also, so I think this design cycle, you get a task, you want to write the code and to run it, and you also take everything into account. So writing the code and debugging it, I think, will be simpler than in other languages, at least for simple things. So I think for this first one, I definitely think they should see some C where you could really touch the bits, and Java, something which is more object-oriented. I mean, Python does support object-oriented, but it's probably also a good thing to do. But I think it's simple enough. The design thing is and readable enough that it's good. And I mean, that's not a proof, but the fact that many other famous universities switched to Python, I think, supports this notion. But you could take this thing. I mean, I think the main theme I'm trying to say is this topics idea, topic-based course. I didn't show any, but some compression. So we take text. I take English text and compress it. I mean, human-generated text. I take this protom and compress it, and we see that Lempel-Ziv works very well on human-generated text, but on this protom, actually Huffman is better, and we could see why, because the repertoire of letters is smaller. So I think these ideas is what I see as the most important thing. Of course, there would be no point in teaching introduction to computer science without programming. That would be, So, and I feel it was a good choice, Python, but I don't think it's, you could replace it by, some probably 5 other, languages of your choice, and probably will be fine as well.
So I noticed in the slides you had like a matrix and what looked like a class, and so how much scaffolding or like code are you giving them, saying like we're going to talk about matrices. Here's a matrix class so that we can.
No, actually the matrices. Oh yeah, we had the matrix class because we had to display it. So actually the metric class was, I think, an exception which we gave them sort of as a black box because it had to talk with T-inter or something. Actually, if you ask me, if it was up to me, it would never happen. So I I've got my strengths and weaknesses. So I definitely needed Rani, who is an expert on. The other alternative was using some of the Python. Python has many packages, but the problem with the package, which would support this, and then I wouldn't have to have this, this fancy. I would just import a package. The problem is that the packages are very well supported by Python 2 point whatever, but Python 3, on some platforms they have it, on some not. So we had to make a decision. So we decided to make something which is self-contained and not. That's actually one of the sour points here. So I'm always debating whether I should use those packages which do zillion of great things or define everything ourselves. And we decided basically we define everything ourselves, except like talking to the graphic system, which there is a limit to what we can do. So Rani wrote this short metrics class and use it. But I think that will be really the only thing that is not self-explanatory. We have other classes like the student class or some other things, but then everything is understood. So, but you have to do some compromises somewhere. So it's.
So I understand that. I think have the book somewhere in my library that Noam Nissan and someone else they developed the course introduction.
Oh, this is Noam Nissan and Shimon Shoken. So they have a very nice thing. It's in Java. They call it, I think, from bits to Tetris or something. So I think there is more. They don't use it as introduction to computer science. They use it like a second year course or something, which sort of simulates hardware and so on. And so I think they did a very good job, but it's not the same. It's not the same thing. Both in the Hebrew University where Noam is and in the interdisciplinary center where Shimon is, they have an introduction, a standard introduction in Java. And this is, I think, even not a required course. I think it's an elective course.
So in some sense, a combination of the two, taking a different
It
stages. So at the beginning,
it could be. Yeah, actually, Shimon is a good friend of mine, and I'm working with him some other teaching projects. And so he taught Java introduction. He said that they're making them sweat too much and something like that. And maybe I should turn this off. I actually consulted with him. I got some feedback from him. He looked at the slides and so on. So I don't know. The course is quite demanding. So it's. I'm not sure if he will switch to that course in his institute, but I'm writing. By the way, I'm planning to write a book. I started writing a book, so hopefully in 2 years I'll have a book. But I think it will be hard to compete with the MIT book which came out. But it's.
Okay, maybe we should take further questions offline.
Okay, thanks very much.